Welcome. This video will show you how to use anti-differentiation by parts. It will show you where that comes from, and it will talk about the purpose of anti-differentiation or integration by parts. Essentially, what you'll be able to do by the end of this video is undo the product rule. A little bit of vocabulary before we start. Integration, for the purpose of this video, I want you to think about integration as undoing derivatives. And because integration by parts is for the product rule, I want to remind you about the product rule for derivatives, which is if you have a product of two functions and you take the derivative with respect to x, you wind up with the derivative of the first function times the second function left alone, plus the derivative of the second function times the first function left alone. This is a fairly complicated mess that comes about because of the product rule for derivatives. So when we undo the product rule for derivatives, it's a fairly complicated process. I also want to remind you about U substitution, which is how you undo the chain rule. This video shows you how to undo the product rule, but previous lessons, the U substitution lesson showed you how to undo the chain rule. So be comfortable with that before you begin this video. All right. The purpose of integration by parts is when you're integrating and you have a product in your integral, you want to solve that integral, and we don't have an easy product rule formula for integrals. In fact, not even every product can be integrated by hand. So when you see a product in your integrand, the first thing you should try is U substitution, because maybe the product came about because of the chain rule. If U substitution doesn't work, then you'll try this new method called integration by parts. And it's possible that you might need a calculator in the end, that maybe neither method will work. Just a quick look at a couple of examples. You should be able to convince yourself that you can do a U substitution on this first integral. I'm going to just tell you that if you use U equal to x squared, you should be able to solve this integral, and you should be able to get 1/2 e to the x squared plus c. So that's a chain rule problem. Remind yourself about in U substitution if you're not convinced of that. The second integral here is not one that you can use a U substitution for. There's nothing logical to make equal to U for U substitution. The second one is one we're going to have to use integration by parts for. Here's where the integration by parts formula comes from. It comes from the product rule for derivatives. If you integrate both sides of the product rule for derivatives with respect to x, remember, if I'm taking the integral of a sum, I can just split that into two separate integrals and take the sum of the integrals. And I'm taking these derivatives all with respect to x. If I simplify that, and on the left-hand side, I'm taking the integral of the derivative, which is basically undoing itself, so you wind up with the product. And on the other side of the equation, notice how these dx's kind of cancel. I wind up with u dv plus v du. So if I move my terms around algebraically, I can wind up with the integral of u times dv, there's that product I was talking about, is equal to u times v minus the integral of v with respect to u. So the integral of u with respect to v is equal to u times v minus the integral of v with respect to u. This is a formula that you're going to want to put a box around, because we're going to use this formula every time we do integration by parts. We're going to do an example. The process you use for integration by parts is the first thing you want to do is figure out which part of your product is the U and which part is the dV. I like to organize my thought with a table. I'm going to have in my table U and dV. Okay. The method for choosing U is called limit. The first thing you should look for is you should look and see if you have any log functions. I don't, so I'm not going to use a log. And then I look to see if I have any inverse trig functions. I don't. And then I look and see if I have any polynomials. I do have a very simple polynomial, and that's going to become my U. You go through limit in order, and the reason we use limit is we're going to be taking a derivative of this side of the table. We know how to take a derivative of log functions. We know how to take a derivative of inverse trig functions. We're hoping that the derivative will make this side of the table simpler. On the other side of the table, we're going to be taking an integral. We don't know how to take an integral of a log function. We don't know how to take an integral of an inverse trig function. So we hope that those functions are not part of dV because we don't know how to take that integral. So limit is in order that this side of the table simplifies when you take derivatives. You'll get better at choosing your U's as you go along. Okay, so the next thing we do is we're going to take the derivative of U. When we take the derivative of x, we get 1. And this will be, just so you know, that's du. We just took the derivative of U, right? Because we chose x for our U, what's left over is going to be dv. So dv is going to be e to the x. On that side of the table, we're going to integrate. And so the integral of e to the x is just e to the x. And just a mental note to yourself, we've gone backwards from the derivative, so that's v. All right. Now we're going to substitute what we have into our formula. So we're starting with this integral, x e to the x dx is equal to u times v. Well, u is x, and v is e to the x. Minus the integral of v, which is e to the x, times du, which is 1. So this makes kind of a greater than sign. So that can maybe help you remember the order that you do it in. So now the whole reason we're doing integration by parts, or we eventually want to have an answer, right? And now look at this. This is something that we know how to integrate. So now we can finish it off. We have x e to the x dx is equal to x times e to the x minus the integral of e to the x dx is just e to the x plus c. Now, that's great. I told you it was true, but I could be lying to you about calculus. So you want to be sure that you could check to see if what I'm doing actually makes sense. And the way you would check to see if this works is you would take the derivative of this answer. If you take the derivative of that answer and you get x e to the x, then it's consistent with everything else I've told you about calculus so far anyway. So I'm going to take the derivative of x e to the x minus e to the x plus c. And this part requires the product rule, which should not shock you. So we take the derivative of x, which is 1, times e to the x left alone, plus x left alone times the derivative of e to the x, which is e to the x, minus the derivative of e to the x, which is e to the x, plus the derivative of c, which is 0. Look at that. E to the x's subtract away, and I wind up with x times e to the x. So my check shows that the derivative of this is equal to the integrand. All right, that's integration by parts. I don't expect you to get it the first time through, but I do have some example videos for you to watch next so you can see the process again.